So in this session we're looking at graphing skills, in particular drawing graphs, and then how to find the equation on a straight line graph. So first of all, drawing graphs, usually you have a table of results, you've got X and Y results, and they're all written down there. And your graph should have, you can extend this like in maths and have all four quadrants here, 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 and let's do that. Here, 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 and here, you know, just extend your axes like so. But we're just focusing on this one for now. You should have axes labels. Let's use some real values. So we'll call this distance. A little bit rough, but you get the idea. Distance D, measured in meters. So we've got three things there. We've got the distance, the name, we've got the symbol, and we've got the unit written. And again, same thing over here. Time, distance gets time. T, measured in seconds. Okay, we've got an origin, 0. In physics, we don't like to have those little breaks in the axes that look like what I'm trying to do there. Those little heart rate monitor kind of beep kind of things, you know. Because when we're drawing our graph, we'll often have a line and we want to know about the intercept. And if there's a break in the axes, that's going to make it hard to work out that intercept easily. Okay, in fact, it's very often, I just say don't do it, tell my students not to do it. But anyway, when we need a title. Okay, a title, the easiest way to do a title for a graph, because students struggle with this so much, is to just put it of the form y versus x for the situation that it's in. So this one, it would be, I'm going to do a short abbreviated title because it's easier and quicker. Distance D versus time T. And this might be for a trolley on a track. Okay, and usually the rest of the, so that's the real title, and this is sort of a subtitle, but to give them more information. And yeah, usually the context of a graph is pretty clear, so you could get away with just distance versus time because you'll have all the rest of the background in your write-up. But anyway, points, so you take them from your table, and when you draw points, this is just keeping it really simple here at this stage. You get into error bars and things later, but you draw a X or a point, or you don't draw a point, you have to draw an X. The reason being that when you draw your line going through all these points, or roughly through all those points, if you've just drawn points and you draw your line through it, you lose the point and you can't see it. So an X shows you where the point really clearly is, makes it easy to see. Okay, so those are the, okay, if I was able to use a ruler on my iPad screen, I should use a ruler if it appears to be a straight line. If it's a curve, you just draw a smooth curve through the points. Let's draw a curve over the top of here. Here's some points. Okay, and an origin happened to have a 0, 0 reading. So I will draw a smooth curve. You don't link the points and make a whole bunch of straight edges. We want to see the general trend, and the trend changes moment by moment. It doesn't go directly from one point to the other. Okay. So finding the equation of a straight line graph, we're going to move our sheet out of the way. Finding the equation of a straight line graph. Here's our graph, drawn a bit bigger, a bit easier to see. And I'm not going to draw my points on it, I'm just going to give you the rough outline to try and keep it really plain and simple. The equation, do I have gradient or equation? I think, oh, it's gone on my sheet, never mind. We're going to find the equation, not just the gradient. The equation is always of the form y equals mx plus c. So we've got distance on this axis and time on this axis. That means D is going to be the y value, T is going to be the x value. They stay as variables. M is our gradient, okay, gradient, or the slope of the graph, and C is going to be our intercept, where our line carries on straight down and intercepts there. So that's C. So C is pretty easy. You can just read C off the graph. But our gradient is a little bit more tricky. What we have to do is we have to look at 2 points on the graph. You should spread the points out as far as possible along this line. And because you've drawn a line of best fit, which if we go back up to our other graph here, our line of best fit here is not necessarily going through all the points. It's just best representation of all of those points. So you can't use those data points when you're calculating your gradient. You have to use new points that are on your line. It's always a good idea, and it's always a good idea not to use 0, 0 as a point, because your line will very rarely actually go directly through 0, 0. And even then, you might be out by just a little bit here or there. So never assume it goes through 0, 0, even if it appears to go through 0, 0. Good idea to shift it up a little bit to, say, somewhere around here where I've done that, and the other one a long way over there. Anyway, so what we then need to do, the gradient is a measure of the steepness of the line. So, and then we talk about the rise over the run, rise over run. So the rise is the vertical distance that it goes up from between the two readings that you're considering from your points. So this is the rise. You might talk about this as df and di. So your rise in this case is df minus di. Final minus initial for any change in anything. And our run is our, let's just move a little bit, our run is ti to tf, or tf minus ti. Excuse me. So we'll end up with numbers for this. Sometimes we talk about triangles and construction lines. When you're doing this in a test or showing it to somebody like a teacher, it's good to draw these constructions on it so that people can see. And when they talk about the triangle, they mean a triangle here, because that's the run, and here to make the rise. So that makes your triangle. Yeah. So then what you do is you take the amount that the rise is, and you divide it by the amount that the run is. And I'll just throw some random values in here. The rise might be, say, 10 meters, and the run might be 2 seconds. So they cover 10 meters in 2 seconds. 10 over 2, that gives us a gradient of 5. Okay, so equals 5. And what do we do with the units for the gradient? It's 10 meters over time of 2 seconds. So now we've got 5 meters per second. Well, we could rewrite that knowing it's a velocity measurement. 5 meters per second, like that. Okay, so putting that back into the equation, and you can replay the video if I went through that a little bit quick. This would be an equation d, which is the y value, equals 5, because it's 5 meters per second. T is our intercept, plus if our intercept, our c value down here might have been say 10 meters there, so let's just make it 1. So c equals 1, so it's going to be plus 1 here. Okay, that's how we come up with the equation. Okay, play that again if you're not sure. Send me questions if you like, and we'll get into some more complex graphing skills at a later time.